Thank you. So this joint work with Vladimir Danilov and Alexander Karzanov. So first, what is TNN matrices? So just explain one part of the title. So consider n times n prime matrices with real entries, and we say that such a matrix M. Maybe it's okay. I will not write any letter for matrix at the moment. Q. So let Q be at TNN. So that means a totally non-negative if for any square sum matrix Q prime, determinant of Q prime is more or equal 0. So interest to such matrices comes in last century. In the middle, it was works by Gantmacher, Krein, Schoenberg. They related to some study of interacting particle systems. Then it was in work in statistics, like Carlin, Efron. But more interesting and more fascinating interest to such matrices comes after Lustig. It's correct. Yeah, it's correct. Then he found the relation between totally non-negative matrices and canonical bases. And then he extended this notion from JLN to other groups. And at the same time, it was, or maybe a little bit later, works by Fomin and Zelevinsky, who were interested in questions. So if you have such a matrix, then so from the definition, you have just to check all square submatrices and check their minors. But they were interested in some questions. So what is the, in some sense, minimal set, which give you certificate that such matrix is totally non-negative, and this comes to cluster algebras. And then later study some combinatorics of Grassmannians, Sasha Postnikov. He was interested in decomposition of Grassmannian in so-called positroid cells, and it was also related to something related to totally non-negative matrices. But I would be interested in questions on quadratic inequalities involved totally non-negative matrices. That means the following. So we consider just inequality such that its quadratic means that we multiple minors of some matrix, and we just multiple two minors. Minor is just determinant of some square submatrix. So we just take some bunch of square submatrices, and then we just consider products of two determinants of them, and then we're interested in the question, then such determinant is non-negative. And one maybe interesting example also from totally non-negative matrices is Jacobi-Trudi matrix. I will explain later what that. And then, so if we have some kind of this quadratic inequality for totally non-negative matrices, then you automatically have this for Jacobi-Trudi Jacobi-Trudi matrix, and then gives you some quadratic inequalities on Schur functions. And so therefore, from this you can extract some interesting relation between Littlewood-Richardson coefficients or embedding of some tensor product of reducible representation, and so on. So what is known about such things? So this famous result by Rhodes and Scandera, which says the following. So if we take, so for any, so we have, for any totally non-negative matrix, if we consider the following quadratic expression, consider n is just denote the set 1 to n. So we consider subsets A, B in n of the same cardinality, and consider the following expression: AB n minus A n minus B. So that means the following. So we consider submatrix with rows in the set A, columns in set B. So we consider determinant of such matrix. We multiply on the complement. So we consider determinant of the matrix with rows in the complement to the set A and complement to the rows B. And then such expression is totally non-negative if and only if it is a non-negative linear combination of temporally leap immanent. So I think it's difficult to explain in school what this, so how to check this condition. And one of the goal of my talk is just explain, to give necessary sufficient condition for maybe more general type of quadratic inequalities, but which you can explain maybe at the last year in the school. So how does this do?
Gleb, just to be sure, any submatrix of a totally inequal of a TNN matrix is itself a totally non-negative?
Yeah, because you consider all minors.
Yes, okay, good.
Sorry, so TNN, so that was a proper matrix, but then you wrote this formula which is a sum, and you say that this is totally non-negative. So
no, it's yes. So means that so it is without it's non-negative.
okay.
Thank you. Too many totally negative. But it is just expressions. Just some polynomial is totally non-negative if you just put inside totally non-negative matrix, then it's negative. So therefore, it was just that this polynomial is totally non-negative. Means that if you just put totally non-negative matrix, then you just get a non-negative number. What?
Will you explain with notion?
No.
No.
No. So the aim of the talk just to avoid.
Finally, I think that the term immanent was proposed by Akunkov, no?
No, it's much earlier. Yeah. So in representation theory, so people know this.
It's very old.
No, I think it's just from invariance, in theory of invariance.
Maybe in another context, I don't know, finally.
I think so. Akunkov, of course, may deal with this, but I don't know his work on this subject, so I cannot comment. Okay, so maybe I will need this Jacobi-True delay, so therefore I can use this place. So so we have now two integers n and prime. So then we have two sets, n, just 1 to n, and n prime. It's 1 to n prime. And we consider by E, n, n prime, we consider the set of pairs ij such that I is subset of n and j is subset of n prime. And they are of the same cardinality. Then for a n times n matrix, so we denote, so which I would just denote here, q, we denote delta q ij. What I just say, it's just we consider submatrix with rows in I, columns in j, and consider determinant of this submatrix. And so for convenience that if I and j are empty, then we put for empty is just 1. And now we consider, we choose 4 sets, x and y, they are disjoint subsets of n, and x prime, y prime, disjoint subsets in A prime, and define the following set C of x, x, y, x prime, y prime. So it consists of all subsets. So it's just a set of all C, which is subset of y. C prime is subset of y prime, such that the following condition holds, that the union x with C is equal union of x prime with C prime, and union of x of the complement to C is equal to the x prime union complement to C prime. So just so inverse. So what would be behind of this? So we just will consider minors of submatrix, but we fix some set of rows x and x prime, and consider minors which has was given C and C prime, also additional rows in C and columns in C prime. And so we consider just kind of this. And then one can easy to see that this set is non-empty. If and only if 2x plus y is equal to x prime plus y prime, and if in particular the difference y minus y prime is divided by 2. And now such now we consider two families, A and B, which consist of elements of C, but we just write this, so it is not subset, but subsets with multiplicities. So we just allow multiplicities in these sets. And now we consider we're interested in the following pairs A and B, such that the following inequality holds. So we consider sum of all A prime in A of determinant of submatrix XA X prime A prime delta Q X Y minus A X Y prime minus A prime, and this is more equal than the sum with respect to B and B prime in B with the same XB XB prime X Y minus B X prime Y prime minus B prime, and we call such inequalities universal totally non-negative if for any totally non-negative matrix this inequality holds.
So what is XA together like that?
What? XA is just the union.
The union?
Yeah, just to make it shorter.
Okay.
So now we to formulate our theorem. So we do the following simple combinatorial construction. So if we have pair C and C prime, so then we just draw on the just circle set C, and then Y minus C, and C prime on the, so we just draw just circle split in two parts, and then C we just put points here just from the one Y, and here just we put it from Y prime, and the C prime and Y prime minus C prime, and so because these guys they belong to one, so this we just so they could be interchanged, so they not necessarily just split into parts, but elements in the C we just color in white, and in C prime we also color in white, and element in the complement we color in black. And so we just get such coloring of sets Y and Y prime with respect to, so if we have Y and Y prime, so Y we just put here, Y prime we go here, and we just color in to and now since now the main definition just to formulate definition. So since Y prime plus Y prime is even, then we can split the union. So just this set, which I just draw on the circle, so we can just draw split it in two element subsets. So we will get matching of this set, but now we just say that the matching is feasible if the following two condition holds. Condition 1, that if the pair belong to the same part of the circle, either down or up, then it have to join two vertices of different colors. And if this pair belong to different parts, then it has to join the vertices of the same color. So this condition 1. So and condition 2. So such. So then we just draw such y plus y prime divided by 2 curves. Then they have to be non-intersecting. And then theorem. I need so the following also I need here before formulate. So for each pair in A, I get the set of all matching, all feasible matching obtained just due to this definition. So we define M of A is just the set of feasible matching. So before theorem. For A and M of B for B. And then the criterion is the following theorem. So this pair of A and B gives a totally non-negative universal quadratic inequality if and only if for any matching M in M of B, there holds that the number of matchings M, so we just, because here matching can be with multiplicities. So therefore we take just matching is M of B and count multiplicity of this matching in A, and then it has to be more equal than the multiplicity of this matching in B, M of B. So you see, so this variant you can explain in the school, and this I'm afraid not. Okay, so now about the proof and some applications of this method. So questions so far?
Why do we call it universal? Because it's a weaker statement?
Universal because it holds for any matrix. Because it could be, so you just get some inequality. For some matrix, you can just choose some numbers, so it's totally non-negative, and then you just put, but it is non-negative, but for another matrix is negative. And universal means that it does not depend on the matrix. And so first I think about this totally non-negative matrices that they are flow generated. That means the following. So we can consider some. We take some acyclic directed acyclic graph, planar G with set of vertices n, just input. So there is n. N would be sources, and n prime sinks, and then you put weights to vertices of this graph, and now you can construct the following matrix with respect to this graph. QG. So you just take i's source and g's sink, and consider the set of all passes in this graph between I and j, and define element ij as a sum of the weights of all passes which goes from I to j. And so weights, you just put weights at the vertex, non-negative numbers. And if you consider such a matrix, then this famous Lindström theorem or lemma, which says the following. So how to compute now a minor of matrix with sets A and J. You have just to choose sets I of sources, set J's of sinks, and then consider sum of weights on the set of non-intersecting passes in G from I to J, and consider weights of just product of weights of such passes on this flow. So you consider flow, non-intersecting flow, and then from this you immediately get that from if you have flow generated matrix, then you get totally non-negative matrix. And this reverse theorem due to Brenti, which says you that vice versa for any totally non-negative matrix, you can find a planar graph and weights such that this matrix is implemented through flow generating. Example. Consider the following graph. It would be infinite, but does not matter. So you just have a rectangular picture. So your graph is just have sources at the x axis, and so you have just n prime, so it would be size of your strip, and sinks are on the top, and the orientation is like this one. So it just each vertical goes up, each horizontal go right, and the small difference with what I just said above, that we just put weights on. No, we just allow this goes here, and we just put weights on arrows, on edges, and we just put. No, we don't need this. So just each vertical will have weight 1, and each horizontal would be take on the height AXI. So just put this. And then one can observe, so if we just go from I to J, then it would be, if you count this set of element of this matrix generated by this flow, then you just get a symmetric function J minus I from x1 to xn prime. And because of this, so there's the entries, it's exactly entries of Jacobi-Trudi matrix, then you just get automatically that Jacobi-Trudi matrix is totally non-negative. Okay. So I just briefly explain so how to prove this theorem. So there's two main ingredients. First, it is just double flows in acyclic directed graphs. For this, we just modify ELSA. So for us, it would be more interesting. We're interested in graph which put weights on edges. So if we have a graph which has weights on vertices, then we just modify it as follows. So we just so I will explain on the example. So suppose we have the following picture. So we have just this would be sources S1, S2, S3, and then there's the sinks T2, T3, and then we have just so this graph, very simple graph. But what we just do, we just split each vertex, which is not terminal, by edge, and then we just from and for each terminal we just put for T we just put horizontal, and for sinks horizontal and for source vertical. So therefore, we just modify this graph to the following. So just maybe I need another color for vertices. So it's through edge, and this is this, and this goes. Yes, it's here. No, it goes here. And this goes, just 1 second. Yes, so this, just 1 second. This goes here, this goes here, this goes here, this goes here. Oops. This goes here, this goes here, this goes here. Yes, so we have 1, 2, 3, 6 vertices, and then we just get 6 edges, and then we just do this, and then we just modify. If we have a flow for our matrix Q, then we modify the graph in this manner, and then with these two sets, so we could just have this CC prime, and then we have a set of sources which would be white for one term. So here we just have these two guys. So therefore they are will get set of white sinks and white sources, and this guy will give us black source and black sinks. And then we just construct two flows, one which correspond to this minor, so it would be just flow of non-intersecting passes goes from white to white, and then in this graph, so it would be another flow which goes to from black to black, and then so if we just so we will have double flow. So just go that something goes like this. It is just for white, and maybe for black goes something like I don't know, like this. And so if we delete common edges, so we have two flows.
It's a bit hard to follow because white and black looks
Okay, so then I just make true picture. Yeah, sorry.
can use some color.
Yeah, I will just make true picture. So we have white, maybe, thank you, black. And then here we have white, and this would be also black. And then we have, so one flow, white flow goes like this one. So this flow goes like this one. And this flow goes like this one. So we have such flows. And then we have to delete common edges. We just delete this, and this. And then after deleting, so we just will get a matching between feasible matching with respect to this definition. So this is white goes to white because this is on the bottom, this is on the top, and this is two different colors, and then they just join it. And vice versa. So for each, if we have double flow, then we get matching in this sense. So therefore, in this product, so how it's related to matching. So therefore, if we just get this product, and this is exactly product of two flows, we get double flow, and from double flow we get matching, and here else the matching, and now there is another procedure, so which rearrange one double flow to another double flow, and then this is just give us the proof of the theorem on one side. And for another side, it would be just proof that if we have that the number of matchings is more equal than the number of matching, then it's non-negative. And in other words, in another side, so there is another lemma which I will explain by picture. So maybe it's not lemma, proposition, okay. So another proposition says us the following. So it's blue. That if we have a matching, feasible matching, inside say M of A, then they exist unique double flow or unique flow for this matching, so it's matching, yes, it's for pair A prime. So then there exists unique flow. We can find such a graph G with unique flow for XA prime and unique flow for X y minus A X prime y prime minus A prime. And then, so if we just have such a graph with unique flow, then we can define matrix. Then we can just put weights 1 for this unique flow, and we get that any other flow is 0. And so therefore for this, so if we just have exit, so if we just have some matching which is here but not here, so then we can construct graph which give us value 1 at M and 0 at all others. So therefore we will get contradiction. And I will just explain you how we construct this. So we just have circle, and we have white, so I just split it, white vertices here, and black vertices, black. Here, and then we have black here, and white here, and suppose we have the following matching. Then we construct the following graph. So just from this matching, so we just join middle edges, and then we just directed it like this one. So this does not exist. This one, this, and this. And then in this graph, you will have unique flow from white to white intersecting. So it's just, and one can check that there is another unique flow from black to black. Okay, so and now what are application? So with this technique, so we can okay. So maybe this is not needed. So there is the following known classical inequality for minors. So if we have Q TNN matrix, square matrix, so n prime is equal n, and we take the same set of, so we have two sets of columns and rows. No, we have two sets of rows, and then we define Q A n minus A. No, just 1 second. Yeah, n minus A. What is? Yeah. Delta Q B n minus B, and then it's more equal. So if we just take Q of A union B, and here you just take union of this, so it would be n minus A prime union n minus B prime, and multiple on Q of A intersect B, And here you just take intersection of these rows, n minus a prime, n minus b prime. So I forgot the name, but very known thing. But now we want to make it a little bit. This is not correct.
No, it's not correct, but we have 5-minute shifts.
Yeah.
So
Yeah, okay.
take the necessary time.
Yeah, so maybe just 2 minutes. Yeah, but now we want to strength this inequality in the following sense. So what we have to add some correction term of the form a n minus b prime multiple on q b of n minus a prime. So just want to swap these guys and just put it in the complementary thing, and then so when this would be universal, such kind of then proposition that this holds. So this would be just holds if and only if A and B are strongly separated and so this notion strong separation was invented by Leclerc-Zelinsky. So two sets are strongly separated. So if A, so if you consider A minus B and B minus A, so that either this is set below of this set or this set below of this set. And also with respect to, because as I, so it was here, so I just told that Jacobi-Trudi matrix is totally non-negative. So if we just apply quadratic, universal quadratic inequality to Jacobi-Trudi, then we get some inequalities on Schur functions. And this, so this is deep result, but this even deeper result that the temporally leap immanence, they are Schur positive on the Jacobi-Trudi matrix. And then, so therefore, if you have totally non-negative inequality, and you evaluate it on the Schur, on the Jacobi matrix, then you get Schur non-negative quadratic expression for Schur functions. And this is important for some questions in representation theory. And for example, one of the famous results by Postnikov, Lam, Postnikov, Pilevsky, maybe this, or maybe too high, I forgot, maybe this, says that if we just take minors, so it just was on matrices, then it's less or equal, so just in another size, then if we just take maximum of AB, maximum means that we just, so this is sets, so for each element we just take coordinate weight maximum. Maximum is A prime, B prime, and multiple delta. On delta Q minimum. Yeah, with our technique, so it's just 2 lines of proof. But then we can also make this sharper, namely, so we can add to this part something which is depend. So we just have from our technique. So we just construct the set of matchings for the left hand side and set of matchings for the right hand side, and then there is some matching M which is here but not here, and then with this matching we can construct make some switch and then construct some another pair, and then we have just kind of this strengthening of this inequality. So therefore applying more deeper result from Rhodes Iskandera, for which I don't know elementary proof because it would be nice, but so what I just read in the literature, so the proof uses theorem of Berlinson and Bernstein on solution some problem. Yeah, so but we can just do with our technique much more things of this type, and important is that you can check it just with computers. So if anyone just come to you and ask if it's TNN universal inequality, so you just can write, you can just draw white black points and then just ask computer to find all pairing for the one side, all pairing of matching for another side, and then just ask him to compare who have extra elements, and then just you're done. Okay, so thank you.
Thank you, Gleb. Questions, remarks or comments or whatever? Yes.
Your inequality are kind of stronger because, I mean, there is no sum on that. Okay, so
no, that is because A in this wait, this inequality. No, there is some.
yes, but on the one that you derive right now.
Here.
Yeah.
Yeah. So this is just So this is just subspecial types of inequality without sum. Yeah, but here then we just made it a little bit sharper. Then you have sum on one side. Yeah, but this is just classical, and this is also in some sense classical. So therefore we just play with them.
Other questions?
Yeah.
Yes. Yes, Marek.
So I come to the inequality because this is mathematics are inequalities. So classical positiveness is just eigenvalue are non-negative. Yeah, this is for self-adjoint matrices. This is you have no, but assumes quadratic for moment. You have some condition of eigenvalue that inequality, or what kind of physics is under this? Because eigenvalue is energy, yeah? But here you have some feeling what that inequality means in physics, or model in physics, I hope.
In modern physics? Yes, so there is
Only what that means in the spectral value, because of course if matrix is not quadratic, you can make quadratic by multiply by conjugate matrix or something like this. But assume for a moment that matrix is self-adjoint. So this is much better property than positiveness, I understand. Yeah. No.
I'm not specialist in matrices.
No, I am.
Yeah, I can ask you. So I can answer. Well, so there is interest.
Understand the inequality. What that?
Inequality, but from. But from.
I always make propaganda. This
But what I can just for me, what is just nice. For example, you have. So if you have inequality, for example, kind of simple case of just this on this. Then if you just try to evaluate it from Jacobi-Trudi, then you have some inequalities of this form. So it is just sum of some sure functions. And but you know, so from representation theory, that this is just sum of C lambda mu kappa S kappa minus sum of S lambda prime mu prime kappa S kappa. And so therefore, if you know that it is short positive, then you know that these Littlewood coefficients, they are satisfy so this property. And this related to the question of Horn, because so if you so how there's a coefficient related to Hermitian matrices. Yeah, so if you have Hermitian matrices A with spectrum lambda and Hermitian matrices B with spectrum mu, so then A plus B, so this is also Hermitian matrices, and then you can ask what would be spectrum. And it has a spectrum kappa if and only if this coefficient, but this is in the physics sense, is non-zero. And for example, then you can extract, so for example, if you know so that if here you have non-zero, so some spectrum value for the sum, then you get that you will get also spectrum, non-zero spectrum value from here. So.
Say to this, now I'm happy.
Yeah, happy.
Thank you very much.
It's okay. We start the speaker again, sorry.
Okay. But it was a question.
Gleb, but to the question of Marek, there probably is a common sense answer about what total non-negativity is physically. When we calculate the determinant, it means that we calculate the oriented volume of a linear map. And what Gleb has in the matrices means that whatever vector subspace, not necessarily for quadratic matrix, whatever vector subspace you take in the domain, it is mapped somewhere to the vector subspace in the target. Always either the orientation is preserved or it is flattened into nothing. That is the physical meaning. Either it flattens or it always preserves the orientation.
So now I'm very, very happy. Thank you.
Oh, good. I'm also happy about that.
For the third time. Yes.